Hi everyone. Today I'm going to present our work on the using submodularity to the data subset selection problem. Well, the outline of the talk will be as follows. First of all, we're going to introduce what is speech data subset selection, and then we're going to show that submodularity naturally captures the problem, and lastly, we're going to see that how good our submodular framework works on real-world data. So to begin with, what is speech data subset selection? Well, let's suppose that we have a very large set of unlabeled speech utterances. Then the procedure of speech data subset selection is to select a subset of the training data and then only label this subset and then train a speech recognition model based on the subset, and lastly evaluate the performance of the model. So a good data subset selection method should be able to select a relatively small subset of training utterances, and also the model trained based on this small subset should be almost the same as the model trained based on the entire set of training utterances. So the motivation for this problem is very clear, right? Because first of all, in order to make the training data useful, you need to label the data. However, transcription itself can be very expensive, time-consuming, and also error-prone. And not just that, not all of the training utterances are actually good, because as we can see that most of them may be very redundant, especially with the speech data. As we can see on the slide, we have like 9 utterances. All of them are taken from a speech corpus, and as we can see, the transcription are almost the same. Although that there is some acoustic variability among these utterances, but the more data you have, the better chance you get redundancy. And lastly, also the more data you have, the longer time you have to spend on training the model, therefore longer experimental turnaround time. So as we can see on this plot, the plot is the performance gain curves of large-scale speech recognition system with respect to the amount of training data you have. And actually this is showing that the more data you have, the better performance the model you can train based on the data. However, it's also showing that the diminishing return effect of this performance gain curve. That is, the new data, when added to a larger pre-existing set of training utterances, becomes less valuable. And the new data, when added to a smaller pre-existing set of utterances, becomes more valuable. And as we will see next, that the submodularity can naturally capture this property. So what is submodular functions? Well, submodular functions is a set function. And then what is a set function? Well, suppose that we have a ground set of elements or entire set of elements we denote as the V that has 9 elements. Then the set function maps from any subset of the underlying entire set to a real value. Then suppose that we have a subset A that has 4 items. Then we assign a value to this subset A. And then, however, notice that potentially there might be like 2 to the size of V that many distinct subsets in total, and the number of distinct subsets grows exponentially as the size of the entire set. Therefore, if you want to optimize a general set function, you may potentially need to enumerate over all of the possible subsets, and that is clearly intractable because it's exponential complexity. However, as we will see, that with the submodularity, we can actually make the discrete optimization problem tractable. So then what is a submodular function? It's a special class of set function. And we say that the set function is submodular even only if that the equation 1 is satisfied. That is, the incremental gain of an element decreases when the set in which that the element is considered grows. And here's an example. As we can see, we say that the function is the number of distinct colors. Then we add a blue ball. Then the left urn has 2 colors, the right urn has 3 colors. When you add a blue ball to the left urn, you get incremental gain of 1. Whereas if you add the blue ball to the right urn, you get no gain because it's saturated on the right urn. Therefore, this function is submodular. And not just because of the diminishing return property that captures the saturation effect of the gain performance curve of many of today's large-scale speech recognition system, but also the submodularity makes the discrete optimization tractable. And that's the key reason why it's widely used in many of today's machine learning applications like the document summarization, sensor placement, and also feature subset selection. In all of the problems, the optimization problem is posed as the equation 2. That is to maximize the set function under knapsack constraint or cardinality constraint. Though for general set function, the objective, suppose that for general objective function f, it's NP hard, we can solve with a integer linear programming technique. However, clearly it's exponentially hard to find the exact solution. And even with the approximate solution, this integer linear programming doesn't have any theoretical guarantee. And when the objective function is submodular, then the problem can be approximated by a very simple greedy algorithm with the approximation guarantee of 1 minus 1 over e. And typically, the guarantee can be much better, depends on the curvature of the function. That is, the more curved the submodular function is, the worse theoretical guarantee is. However, the less curved the submodular function is, the better guarantee it can get. And also, thanks to the submodularity of the objective function, we can get almost linear time complexity to solve the greedy algorithm. And lastly, none of this is possible without the submodularity. So here's an example that when we apply some submodular functions to subselect the synthetic data on the two-dimensional case, then we see that the selected elements is looking like this. They very well span the overall space of the two-dimensional space, and also they can be very good representative of the overall two-dimensional space. And having seen that our submodular framework worked very well on choosing elements in the synthetic data, now the question is, how well does it work empirically on the real-world data? We tested our approach on we evaluate our approach on subselecting data from the Timic corpus, and for each of the selected subset, we train a 3-state hidden marker model, and then the performance of the model is evaluated on the quartet set of 192 utterances. And as we can see on this plot, we compare our submodular framework against two different baseline methods. One is the random baseline. What it does is to randomly select subsets and then evaluate performance only based on the subset. The other is the histogram entropy baseline. What it does is to select a subset of utterances that maximizes the entropy of the distribution of the phones. And as we can see, along all of the percentage cases, for different sizes of the subset, our submodular framework actually can select a better subset that yield better performance. And especially for the small percentage cases, like from 1 to 10 percentage cases, we get significant improvement over baseline method on subselecting data. And in this plot, we compared between two submodular functions in terms of subselecting data on the real world, on Timic corpus. And as we can see, that the facility location function works better than the saturated coverage function for different subset sizes. And lastly, to conclude our work, we can firstly say that submodular function, the submodularity framework, works very well, and also it works much better than the other baseline methods in subselecting data. And secondly, submodularity can naturally capture the diminishing return effect that we see in many of today's large-scale speech recognition systems. And therefore, it's a natural fit for the speech data subset section. And lastly, our submodular framework has the theoretical guarantee, and also because of the submodularity in the objective, we can have a very fast implementation. And that's it. Thank you very much.